Welcome back. So, you should have just watched a video discussing Dalton's atomic theory. And one thing you'll notice in that video that's maybe different than what you saw in your textbook, or how we'll discuss it here, is that in that video they broke Dalton's atomic theory down into, I think, 7 postulates, right? But our textbook only breaks it down into 4. And this is pretty common with Dalton's Law. You'll see some books might even have 6 or 5. It's just how they sort of break apart the information. What this textbook does is it combines some of them into one statement, which may have been broken down into multiple statements in other locations. But the same basic ideas. And so what I'm going to do is go through the 4 fundamental ideas, the 4 fundamental tenets of Dalton's theory that are presented in our textbook, which encompasses information. So what Dalton said was that, first of all, each element is composed of tiny, indestructible particles which he called atoms. Now, as you've seen, and we'll see maybe in the videos, Dalton isn't getting all of these ideas that he's going to come up with out of his head, right? He's being a good scientist, right? He's relying on data that was already collected, what other people are doing, and he's compiling, if you will, these ideas together, making connections to have some sort of cohesive theory. So while we always present these as, Dalton's theory or this, but he's building upon what other people have done. So, for example, right, the idea of atoms comes initially from the ancient Greeks, right, in terms of the term atomos, which you see. And we'll see with some of these other ideas that he's using the work done by others and just putting it into a framework, if you will. So, first one, tiny indestructible particles called atoms. Now, these atoms have certain commonalities. And what he pointed out was that all atoms of a given element have the same mass and properties. So in other words, for example, all carbon atoms are the same as all other carbon atoms. Or all iron atoms are the same as all other iron atoms. So the atoms of a given element are identical, according to Dalton. Now, however, they are fundamentally different than the atoms of other elements. So, while all atoms of a given element have the same mass and properties, they are distinguished from atoms of other elements. So in other words, while all carbon atoms are the same as all other carbon atoms, and all iron atoms are the same as all other iron atoms, there's fundamental differences between a carbon atom and an iron atom, right? They are not the same. So all atoms of a given element are the same, but fundamentally different from atoms of another element. The third one, atoms combine in simple whole number ratios to form molecules, or to form compounds. Right? All this simply means is that we have whole numbers of atoms, right? We can't have half an atom combining with something. So if I have something like H2O or CO2, right? We have 1 oxygen to 2 hydrogens, or 1 carbon to 2 oxygens, right? What we're not going to have is hydrogen 2, oxygen 1.5, or carbon 0.5, oxygen 2, right? We're not going to have fractional atoms, right? They're always going to be small whole number ratios of the elements. And then finally, when a chemical reaction occurs, or chemical change, atoms of one element cannot change into atoms of another element, right? So we talked about in the last section about conservation of mass, where matter or mass is conserved over the course of a chemical reaction. And so what that means is if we start out with, just to pick a number, 10 carbon atoms, in the in the beginning, we're going to end up with 10 carbon atoms in the end, because we have to conserve the mass, and elements can't change into other elements. So if it starts a carbon atom, it's going to end up as a carbon atom. It starts nitrogen, it's going to end up as nitrogen. Right? Carbon will not change into nitrogen in a chemical reaction. So Dalton put forth these sort of fundamental ideas that would serve as a guide for future work, looking at the structure and how atoms behave. Now, in terms of a physical model of the atom, right, this is another important idea, right? We can have these ideas, but it's also sometimes it's important to have some sort of physical reference. And Dalton gave us sort of the first physical reference, and this referred to as his billiard ball model, which is extremely simple and basically follows the first tenet of his theory, is that he visualized atoms as tiny indestructible particles similar to what we know or what he would have known as a billiard ball, right? So this idea that they're hard, they bounce off one another when they hit, right? You know, this was his model. Now, the other idea that he sort of built upon with this is he knew that these atoms were not charged. In other words, the atoms were neutral. Now, he didn't really know much beyond this, except what he talked about in his theory about how they sort of behave when they combine, and how, you know, a carbon billiard ball is different than an iron billiard ball, different than a gold billiard ball, etc. But this is the place where we started. And so in upcoming videos, you'll see, we'll look at important experiments that led to the development or advances in atomic theory. We'll look at new models of the atom that were developed as we gain more and more information, and as this theory evolves to what we know it as to today.